Hello everyone, welcome back to Electronics 1. What I want to do in this class is look at a common emitter amplifier example and perform an analysis to determine the small signal gain of the amplifier. And we'll do it first with out using a small signal model, and then we'll do it again with a small signal model to show the advantages. So to design a common emitter amplifier, we need to bias the bipolar junction transistor into the forward active mode of operation. And I should stress the fact that these models that have been developed, these T and hybrid pi models that we've developed, are assuming that we're operating in forward active mode of operation. Okay, so we bias, our first goal is to bias the BJT to make sure it's in forward active mode, and then to add some small signal perturbations to VBE and assess how those are amplified by the system. Okay, so let's look at a very simple common emitter amplifier. So we call this a common emitter amplifier because, as is hopefully obvious through the configuration, is that the emitter is common to both the input circuit and the output circuit. So we're going to take our output from the collector, and our input is let me include both the bias signal on the input and that small signal that's going to be associated with those small perturbations. So here's our small signal component, and here's our bias signal that's going to ensure that our device is in the forward active mode. And as a result of these two signals, we'll get a output voltage. In this case, maybe we'll consider the output voltage as the collector to emitter voltage. That's a function of the combination of those two input signals. Okay, so first, to control the operating point, VBE is applied, right? This bias signal is applied such to set the collector current at IC. This point will define our operating point, which we generally refer to as Q. So in the last class, we looked at that operating point graphically here on our characteristics that shows our input behavior. So this is looking at the input circuit. So here we see the input of applied VBE that determines the corresponding collector current as a result of that input bias signal. We can also look at the operation and the bias point from the perspective of the output. So, and for this specific circuit that we've shown here, we can look at the operating point from the output perspective, as shown here, and we see that again, now this diagram shows that while we have this operating point that was defined based on our input circuit and our applied bias signal, and that kind of determines which one of these family of curves we fall on, and then the output circuit, and in fact our collector resistor is going to define the this operating characteristic, or this load line here, if you will call it that. And this, if we extend this, we'll see that that load line intersects the y-axis at VCC over RC. Okay, and we'll note that this operating curve or is set by those parameters. Okay, so the DC bias and that signal VBE puts us at specifically this point and this collector current, but then the fluctuations in VBE that are shown here, those move us back and forth across around this line to generate in this case, what we've defined our output as the collector to emitter voltage that fluctuates correspondingly as depicted on this plot. Okay, so this plot is representing the output circuit's behavior in response to those small signal fluctuations. The textbook uses an additional approach that kind of represents both the input and output at the same time through this what's known as a voltage transfer characteristic. So here we have a voltage transfer characteristic for this specific circuit that's shown on the left here, and I'll note that this VBE is in this diagram is representing both the combined small signal and the bias signal in a single source there. So this voltage transfer characteristic makes it easy to visualize the response of the output as a function of the input. So I'll often use the acronym VTC to depict or define the voltage transfer characteristic. So here it's interesting to note that the changes in VBE, how they impact the getting into the various operating regions, cutoff, active region, and saturation. So when VBE is too low, such that your base to emitter junction is not forward biased and it's not on, well, then we have the transistor essentially shut off, and the collector to emitter voltage is just sitting at VCC, right? Because this essentially appears as an open circuit because it's essentially turned off. Okay, so the voltage at this point just becomes equal to this. But as we increase the voltage to where the base to emitter junction starts to become forward biased, we move into the active region, and we'll see that as the transistor starts to turn on, we start to conduct current through the transistor, and we get more and more voltage dropped across our collector resistor, and therefore the voltage at the output, the collector to emitter voltage, drops until, with sufficient collector to or base to emitter drive, so if we drive this junction sufficiently hard, we'll get sufficient collector current flowing through this collector resistor that the output will drop, and they're showing 0.3, 0.2 volts, but we get to a point where the transistor becomes saturated. Okay, so we enter our saturation mode of operation, and now the transistor just has a fixed voltage drop across it of about 0.2 volts. Okay, and we're no longer acting as an amplifier; we're just acting as a closed switch. Okay, so the voltage transfer characteristic is a nice means of representing moving through those different modes of operation with varying levels of base to emitter voltage, right? And it's when we aren't using the device as a amplifier and we're just using it as a switch, we tend to cycle between having no base to emitter voltage to having a high level of base to emitter drive, so that we switch back and forth from cutoff to saturation. And this is again when we're using a transistor simply as a switch, which is common in many applications these days, and it might be common if you're driving this from a logic level output where you're just trying to turn the transistor on and off to control the on and off state of some device. Okay, but let's move on, and let's analyze and see if we can calculate the gain of this circuit from earlier here. So if I can grab this circuit here, let's just bring it along with us so we can refer to it. And maybe I'll just drag this over here. And let me just get rid of those. Okay, so we could calculate the output voltage from this circuit by doing a simple KVL analysis, or really just calculating the voltage drop across this collector resistor and taking that, subtracting that from the voltage source VCC. Okay, so VCC minus the drop across that collector resistor, and that drop is going to be a function of both the small signal component and the bias component of the collector current. Okay, so this will give us a total VCE output voltage, right, where part of it is due to uppercase VBE, or our bias, and the other is due to our lowercase VBE, or our small signal component. Okay, through a little bit of rearranging here, I can write this in terms of the collector current, or the sum of these collector currents, and I see that I'll get an expression that looks like this. And I want to note that this this collector current here, maybe I should write it up here, this is the total the collector to emitter voltage here. This is the total collector to emitter voltage that results from both the bias and the small signal. Okay, and again, this here is my total collector current, my sum of my current due to my bias and my current due to my small signal perturbations. Okay, so if we consider the total collector current as being a sum of the large signal and the small signal, then we can break the components of this equation up as follows. Okay, so I'm just going to pull out the large signal components, so the uppercase IC, and that is that is a result of VCC and RC. There's no small signal component in that term anyway, and a result of 1 over RC times VCE. Note that this is the large signal VCE, right? So this is the large signal component of this, right? Where this is the combined large and small signal. Okay, and VCE here, if I rearrange this this back kind of in this original form that's shown here, VCE, the large signal VCE, is simply equal to VCC minus the drop due to the bias collector current IC. Okay, and if so the only component of this equation that the small signal collector current is a function of is the small signal component of this VCE term. Okay, so drawing that out, I can see that IC, the small signal component, is simply equal to, right? Oh, sorry, I think I have an error here. This should be a negative sign here. Sorry. So just note that negative sign. So if the only component that of this original equation that has a small signal component is this VCE, and so that is lowercase VCE divided by RC. Okay, again, that's just coming from the small signal component of this term of the equation, including the minus here, I guess. Okay, so that's what contributes to the small signal collector current. Rearranging this, I can write my VCE, which we defined as the output of my amplifier, is equal to minus RC over IC. So all I've done is rearrange that equation. We will recall that the collector current is the small signal collector current is related through the transconductance term to the small signal base to emitter voltage. And rearranging further, I can write this in terms of a gain, right? So this is a voltage gain, small signal voltage gain here, where my output over my input. So my output is the small signal collector to emitter voltage. My input is my small signal base to emitter voltage. So with that rearranging, I see that my gain here is equal to my transconductance times RC. Okay, so I've just calculated the small signal gain of this common emitter amplifier that we started with. Okay, and again, this is the as gain is defined, it's our output over our input. You might note here that the gain is inverting. So note that the gain is inverting because as the collector current increases, and I'll just say due to increases in VBE, VCE, the output, decreases. Okay, so that's where the negative comes into play. Okay, let's redo this analysis one more time, but let's use our small signal models. So let's repeat using model approach. Okay, so I'm going to take my, let me just paste in my circuit here again. Oops. Try this one more time here. So I'm going to take that and represent it in a small signal model. So again, I only care about the small signal components because what I'm interested in is the small signal gain. For this example, I'm going to use a T model. Okay, so I'm going to represent the transistor with this T model where I have an intrinsic emitter resistance between the base and the emitter, and I have this controlled current source in the collector circuit. Okay. Now, from a small signal perspective, when we convert our models, our circuits to a small signal model, all of our DC sources we simply short to ground. Okay, so from an AC or small signal perspective, this signal, this DC component gets shorted to ground, and this, although we've shown this VCC here as just a bar here, remember that this VCC is coming from some DC source, VCC. And so from a small signal perspective, we're going to just short out these sources. Okay, so short DC sources when doing small signal analysis. Okay, so with those shorted out, maybe I'll draw these in a different color. These external components, so I've just bypassed that DC source, and here's my small signal source, VBE. My collector resistor. Now again, if I'm going to short out the source VCC, then my collector resistor I can just show being connected to ground, and of course my emitter was always connected to ground. So this is my my circuit using a small signal model, and my output here is taken right off my collector. So in fact, this is my output here, which is my collector, my small signal collector to emitter voltage. Okay, and again, just note here that this is connected to ground because of this signal being shorted, the DC source being shorted when doing our small signal analysis. Okay, so let's analyze this circuit. This using this model, the circuit is much more simple to analyze. So VBE is equal to IE RE, right? And maybe I'll label IE on here. So here is my small signal IE. This is IC here. This is IB if we care. Okay, and I know that IE is related to IC as IC divided by alpha. Okay. I also know if that VCE here is, so my collector current, I'm going to extend and show that this is my collector current, right? This is a series circuit here, so this collector current is flowing around here. So I can also see that my output voltage VCE here, which is the voltage across this resistor, is going to be equal to the negative of my small signal collector current times RC. Okay, so rearranging this in terms of IC, I can show that minus VCE over RC is equal to IC. I can substitute this in here. And I get an expression, for VBE that looks like minus VCE over alpha times RE over RC. Okay, and what I really want this equation to be in the form, so to get a small signal voltage gain, I want it in the form of the output over the input. So rearranging this equation above, we should see that the expression becomes minus alpha divided by RE times RC. And in our last class, you'll recall that we defined the small signal parameter, the intrinsic emitter resistance parameter, as alpha divided by GM. So substituting this into here for RE, I get a small signal gain that's minus GM times RC. Okay, and lo and behold, that's the same small signal gain that we found up above here through a fairly more complicated procedure. Okay, so here we see the benefit of the small signal model in arriving at the small signal voltage gain of a simple common emitter amplifier. Okay, so we'll leave that there for today. Coming lectures, we'll look at assessing some of the other properties of amplifiers that we're interested in: input resistance, output resistance, and we'll look at configuring our amplifiers into different configurations. We've only looked at to date common emitter, but we can configure our BJT amplifiers into common base amplifiers or common collector amplifiers as well.